Okay, in this video, I'm going to talk to you a little bit about how to solve trigonometric equations. This week in Math Excel, you're going to see lots of application problems, and in the process of solving these application or real-world problems, you're going to need to solve trigonometric equations and find all solutions to those equations. In example number one, we're not actually solving anything. We're just being asked to check whether a given number is a solution. So we've got to determine, does theta equal pi over 4? Does that represent a solution to this particular equation? And after we check that, we're going to do the same for pi over 6. So let's just remind ourselves that this theta value is our independent variable. That could be any number that we would like. We're going to investigate to see whether or not that number, this angle measure, satisfies this equation. So it's really pretty straightforward here. 2 times sine of pi over 4 minus 1. We would like to see if it's equal to 0. Now I would challenge you to do this without a calculator, and as long as you have your unit circle memorized, then this shouldn't be any challenge. If you've forgotten all of the components of your unit circle, it would be a good idea to go back and take a look at it. So anyway, to simplify this, I would follow the order of operations and complete any multiplication first. Now, in a sense, this trigonometric equation right here operates at the level of exponents in the order of operations, so I'm going to simplify it first. So if we're thinking about the order of operations, exponents have to be done before multiplication and division, and that's done. Those are both done before addition and subtraction. So sine of pi over 4. Well, I'm going to think of a unit circle here, and the position pi over 4 is at this spot right here, and sine is asking for the y coordinate at this position. Well, that's the square root of 2 over 2. So we now have 2 times square root 2 over 2 minus 1. I can complete the multiplication and division now, working left to right, if there was any division. I see that this 2 times square root 2 over 2 is just the square root of 2. And clearly the square root of 2 is not the same as 1, so root 2 minus 1 is not equal to 0. So we would say that pi over 4 is not a solution. Not a solution. And if we do the same thing for pi over 6, let's see if I can squeeze that in this space here without moving. I can use this prior problem as a point of reference. 2 times sine of pi over 6 minus 1 equals 0. We're testing to see whether pi over 6 is a solution. Now, pi over 6 is the first angle measure right here before that pi over 4 measurement, and the y-coordinate here is 1/2. So after I make my substitution here, after I complete this simplification, we've got 2 times 1/2 minus 1 equals 0. Oh, well, 2 times 1/2 is 1, and 1 minus 1 is 0. So yes, we can say that pi over 6 is a solution. Now, technically, it's not the only solution. That's why we're saying that it's a solution. And again, being technical here, there's an infinite number of solutions, and we'll talk a little bit about how to obtain those by looking at example number 2. So our job is to solve the equation cosine of theta equals 1/2. So find the theta values so that cosine of theta is equal to 1/2. Now here again, I'm thinking about a unit circle, and when I look at a unit circle, there are two positions that come to mind that have a cosine value equal to 1/2. This is our x-coordinate that's equal to 1/2, and that's this position here and here. The last angle before vertical and the first angle after vertical on the bottom of this unit circle. And so this position here is 60 degrees, also known as pi over 3 radians, and this position down here is 300 degrees, or 5 pi over 3 radians. Now, normally when I write these questions and I give them to my students on paper, I will usually add this phrase at the end after we ask you to solve the equation. I'll usually say something like this: on the interval 0 less than or equal to theta less than or equal to 2 pi. And what this phrase does is it limits our answers to the solutions inside of a unit circle. However, this particular problem doesn't say that, and I wonder if some of the Math Excel questions do the same. They'll actually ask you to give a general formula for all of the solutions. And what we mean is this: certainly pi over 3 was one solution. This angle measure here was one solution. But as you recall, we can continue adding angles to this, or we can add an angle measure to this and complete another rotation. And so not only is pi over 3 a solution, but another rotation around the circle is also a solution. So if that's 1 pi over 3 and we add 2 pi radians, or 6 pi over 3 radians on top of that, then another angle measure is 7 pi over 3. That's a full rotation plus another pi over 3 radians. Then we can rotate again and again and again, and we can create an infinite list here. So we'll just add one more to emphasize this point and indicate that that set of solutions can go on indefinitely. Similarly, down here, we can do the same thing. Certainly, this position right here was a solution, but if we rotate an additional time around the unit circle, then we have another solution at 11 pi over 3. That's just one full rotation, or 6 pi over 3 radians beyond the initial solution. And again, we can do that, 17 pi over 3, and so on. So rather than trying to write an infinite list like this, we can come up with a general formula for all the solutions. And for one round of the solutions, we might look like this. Theta is equal to pi over 3 plus 2 pi times k, where k is an integer. K is an element of the integers, and I'll use this double bar z to represent that. So as long as we pick an integer value, say, remember 1, 2, 3, and so on, we could use negatives. We could also include the number 0. That's what integers are. They're all numbers without any decimals. As long as I pick a number from that list and place that in place of k here, then 2 pi, which is a full rotation, times this integer value plus this original position, pi over 3, would represent an angle measure in this position on the unit circle. So that k value, again, is indicating the number of rotations beyond or prior to that position in the unit circle. The other solution or other answer to this particular problem is starting at 5 pi over 3 and adding rotations beyond that. So this is a common way to indicate all solutions by giving a general formula. Moving on, let's take a look at another example here. This time we're solving the equation, and the instructions did provide us the limitation here. So this is their way of saying that we only need the theta values that exist inside a unit circle, between 0 radians and 2 pi radians. Notice that we're not going to include an answer if it does land precisely on 2 pi radians. We know that 2 pi is the same as 0. So if our solution comes out to be 0, we're going to include the 0, but we're not going to include the 2 pi radians. All right, so here we go. If we're going to solve for theta, theta is our unknown this time. I'm going to work backwards through the order of operations. And I do this all the time when when I'm solving an equation. When you're simplifying an equation, you go forward through the order of operations, but when you're solving an equation, you work backwards. And so what this reminds me is that I should do any addition and subtraction first in order to isolate this variable. And so one thing that I can do is subtract the square root of 3 from both sides of the equation. And it doesn't look like there's any more addition or subtraction necessary to isolate this variable, so I'll move on to multiplication and division. And certainly I can divide both sides by 2, and that's going to leave me with sine theta equals negative radical 3 over 2. Now, as I said a few moments ago, trigonometric functions essentially operate on the same level as exponents. So I'm here now, and I would solve the exponent position last. Here again, I'm not going to reach for a calculator. I'm going to do this without a calculator, and this equation is actually quite easy to solve, again, if you've got your unit circle memorized. Sine of theta equals negative radical 3 over 2. Well, this is our way of asking where in the unit circle does the y value equal negative radical 3 over 2? And that's in these two positions here and here. Because of the limitation before, because of this domain restriction, we're not worried about multiple trips around the unit circle. We're only worried about one full rotation, and all we have to do is identify the positions inside this unit circle that satisfy this particular expression. And so we're looking at the last position before vertical and the first position past vertical in the third and fourth quadrants. And so that to me looks like 4 pi over 3 and 5 pi over 3. And this would be the best answer to provide. Now some of you might be wondering, well, what if I measured off of the positive x-axis but in a clockwise rotation? Couldn't I say that theta is equal to negative pi over 3 and negative 2 pi over 3? And to that, I would say, technically, you're not wrong. I mean, you're absolutely right. This is negative pi over 3 radians, and this one is negative 2 pi over 3 radians. But what you got to keep in mind is that we were told from the beginning that our solution has to exist between 0 and 2 pi. And while these positions represent the same as these positions, these numbers are not between 0 and 2 pi. So this is below 0, and this is also below 0, and that's why we would not want these as a solution. These are your best bets. Moving on, I've got 2 more problems. The video is getting a little bit lengthy, but I think it's worthwhile. I'll go ahead and finish these 2 out. For this problem and the next one, we should notice that there's something different occurring here. Inside of the argument of the trig function, we don't have just theta by itself anymore. We've got 2 theta here, and down below, again, theta is not by itself. We've got theta minus pi over 2. So anytime that happens, what I like to do is I like to rewrite the expression on the left side or wherever it occurs. Instead of using 2 theta, I'm going to make a note here, and I'm going to call this alpha. I'm just going to call it a different letter here. You could even use x if you wanted to. Sine of x is equal to 1/2. And just make a note, a mental note, or off to the side. This x value that we're solving for is technically equal to 2 theta. So when we're done, and our job is to solve the equation in terms of theta, we're going to come back and reference this note, and you'll see what I mean when we get there. Now here again, the instructions say that we want all solutions between 0 and 2 pi. So this problem, written this way, isn't too hard to solve. Where in a unit circle do we have a y value equal to 1/2, positive 1/2, and that occurs here and here. First position past horizontal and the last position before horizontal in quadrants 1 and 2. So my solutions are pi over 6 radians and 5 pi over 6 radians. And that's the solutions in terms of x. But do keep in mind that x was equal to 2 theta. So let's go ahead and make that substitution back again. We've got 2 theta equals pi over 6 and 5 pi over 6. And remember, this notation on the right-hand side is just listing multiple solutions. I could, if I wanted to, create multiple equations that represent these solutions. I tend not to do this, but if you wanted to, for clarity, you absolutely could. Now, lastly, in order to get theta by itself, let's divide each of these by 2. Both sides of the equation on each of these equations divided by 2 leaves us with a theta value of pi over 12, and a theta value of 5 pi over 12. Now, that's all well and good, but there is a catch. These two angle measures, pi over 12, we don't know exactly where that is on the unit circle. We never did memorize that, but it's this position right here. It's very, very close to horizontal. And 5 pi over 12, well, that's just before vertical, and that's right here. Those aren't the only solutions to this equation that exist in this domain. We didn't see them yet, but there are going to be 2 more. And let me see if I can make that argument this way. I'm going to jump back to this x line for just a second. So certainly not only did pi over 6 and 5 pi over 6 represent solutions, but we could have also extended this as well. We could have gone a bit further and, perhaps a whole nother rotation around and said that 13 pi over 6 and 17 pi over 6 and so on, those could have been solutions as well. So one full rotation, or an additional 12 pi over 6 beyond 1 pi over 6, that would represent the next solution in this position. And then if I had 5 pi over 6 plus 12 pi over 6, again, this is just some common denominator form of 2 pi. This is where the 17 pi over 6 came from. We've got another solution in that position. Well, the reason why I want to consider those is this, because if 2 theta is equal to 13 pi over 6, and if 2 theta is equal to 17 pi over 6, then when I divide these by 2, divide that by 2, by 2, divide all of these by 2, now I've got an interesting result. I've got theta equal to 13 pi over 12, and I've got theta equal to 17 pi over 12. And as it turns out, 13 pi over 12, well, that's just a little bit beyond horizontal in our unit circle. That's this position right here in between the 7 pi over 6 position and pi. So we've got 13 pi over 12 and 17 pi over 12, which is right here. And these two angles do exist within a unit circle. These two in this particular form exist within the unit circle. So we actually ended up with 4 solutions to this problem, not just 2. And to make a long story short, when you've got this multiplier here, this 2 essentially tells us how many trips around the unit circle, the number of trips around the unit circle that this x value is going to have to spin in order to produce enough solutions at the very end. So I stopped here with my x values. These are the 2 results in the first rotation around the unit circle. These are the results for the second rotation. Had this number been 3 pi, then I would have done a third set of potential solutions here as well. So that's a bit of a hint when you see these problems. Now, lastly, for this example, there are a couple ways we can solve it. We can use trig identities, such as the difference identity for tangent, and solve it. But again, what I like to do is rewrite this. Tangent of x is equal to 1. And we ask ourselves, well, where does tangent of x equal 1? Well, that's this position and this position. So x is equal to pi over 4 and also 5 pi over 4. And again, these are the two solutions that landed in a unit circle, and that's what our restriction up here was telling us about. Now keep in mind that we're not solving for x. I should have made a note. I did make a mental note, but I didn't write this down. X is what I'm using to replace theta minus pi over 2. So I really need to say that theta minus pi over 2 is equal to pi over 4 and 5 pi over 4. So if I work to isolate theta at this point, then I'm going to add pi over 2 to both sides of the equation. And technically I have two equations here. One is equal to pi over 4 and one is equal to 5 pi over 4, so I'm adding it twice. And we see that theta is equal to, well, pi over 4 and pi over 2 need a common denominator, so I'm going to write those this way. I'm going to say that we've got pi over 4 plus 2 pi over 4, that's a half. And we've got 5 pi over 4 plus 2 pi over 4. Pi over 4 plus 2 pi over 4 is 3 pi over 4, and that number exists in our unit circle, which is a good sign. And 5 pi over 4 plus 2 pi over 4 also exists in our unit circle. That's 7 pi over 4. And these two solutions exist in the unit circle. Had we chosen any other angle measures beyond a unit circle rotation, say 9 pi over 4, that would have been our rotation beyond this guy. Or if we had used, let's see, 8 plus 5, that's 13 pi over 4. If we had used those as additional positions around the unit circle, then even by subtracting 2 pi over, I caught myself here, even when we subtract, sorry, I did it again. We're not subtracting pi over 2 or 2 pi over 4. We're adding 2 pi over 4. If I were to add pi over 2 to these numbers, that would have produced solutions that are well beyond the unit circle itself. So I would stop here with these solutions, knowing that they are the only results that exist inside the unit circle. I know it's a bit tricky to think about these, especially the last two examples, so if you have any additional questions and would like to meet in real time using Zoom or Google Hangouts, please send me an email and we'll try to set up a time to meet during my office hours. Thanks for watching.